Going to have a talk of Renato Dupke, who is going to give a talk about, I don't have the title of your...
JPAS.
JPAS, okay. Renato, please share your screen.
Can you see my screen? No. Oh, I haven't shared yet, right? Okay, just a second. Can you see it?
Great, yes. Thank you. You can start.
Right. Fantastic. Good afternoon. And before I start, I'd like to thank the organizer of the meeting, Rogerio, and for the invitation. And it's a pleasure to talk to you about, give you some updates about the JPAS project here. And that's actually the second time that I'm doing this, because once I came, when Rolf invited me to do it, I think it was 2013. And the project was just starting then. And he was very interested in the potential of the project. So I think that by now, many people here from JPAS that I've seen already. So I believe that most people, or a lot of people here, know about the project. But JPAS, it stands for the Havalambre Physics of the Accelerating Universal Astrophysical Survey. It is a collaboration of 4 institutions, 2 from Spain, 2 from Brazil. In Spain, there's okay. In Spain, CEFCA, Centro de Estudios de Física del Cosmos de Araguán, and it's where basically the data center, the main data center, and the nearby observatory was built specific for JPAS. And this institute, in part, was also pretty much based on JPAS-related matters. And the Institute for Astrophysics of Andalusia in Granada, and in Brazil, the National Observatory, and the IAG, University of São Paulo. So here I'm listing the collaboration board of the JPAS, Javier Senaro for CEFCA, myself from UEN, Raul Abramo from the Physics Institute, University of São Paulo, and Pepe Vilches from the Institute of Andalusia, Astrophysics of Andalusia. Silvia is the science director together with me. And basically, JPAS is a unique experiment in that it has a very hypertrophic usage of filters, narrowband filters. So it has 56 narrowband medium band filters, 54 narrow, 2 medium, and the other broad ones that everybody uses. And the precursors to JPAS in terms of that, they're not exactly precursors because they appear pretty much at the same time. I have J+, which I'm going to talk a little bit, just mention briefly. It's a small version of JPAS with 12 filters, 8 narrowband, medium band filters to study the local universe. Its counterpart in Brazil, in the south, the S+ survey, the science director of which, Roderick, I think, is here. And it's called now PAUS, Physics of the Accelerating Universe Survey, which is a project that started with JPAS. And then there was one group for PAU, and then they broke in 2, and one became JPAS, the other one became a small version, which is called the PAU survey with 40 narrowband filters. The area is relatively small. Both J+, S+, and JPAS, they have very large areas. And a real precursor of JPAS, also done with many common people, was the Alhambra survey with a very small area, 3 square degrees, and 20 narrowband filters. And you can see the paper by Molas et al. 2008 describing the results. And it was a lot of, and Molas is one of the founders of JPAS as well. So basically, this project, what they're doing is trying to recover this, observing this, but with a ridiculously huge number of narrowband filters, which nowadays can be actually done with very nice throughput and and the limitations that allow us to do this. This study was proposed originally. The idea came from Narciso Benitez, 2009. That's a paper that I quote for him, which was a long time ago, but it shows that even with, at that time, without a lot of information what we know now with respect to technology of filters, he showed that going out of the standard, 4 or 5 filters that people use to get photo Z from in surveys, you start increasing the number of filters, you start improving. Here's the error in delta in Z in redshift. You start improving significantly the errors that you get here, achieving 1%. We in JPAS, we are about here, and we're achieving what was intended, the goal, and has been tested with the miniJPAS, which is 0.3%, 900 kilometers per second. So this combined with clever use of odds to select if you have a large number of galaxies, you can actually select those who have the best peaks for knowing the photo Z. And if you use that, you can select the high odds galaxies, and you can increase significantly your photometric redshift depth. Okay, so so you can get further. Here's at about 0.95. Now simulations show that we can get probably to 1.2, depending on the type of galaxy we use, once we get all the filters observed. And of course, this idea originally was thought of being applied to improve cosmological measurements, in particular, the radio baryonic acoustic oscillation measurements. And we know that the angular bow, BAO, has been observed, but the advantage of getting the radio bow is that you can reduce the uncertainties with respect to the constraining the cosmological parameters. For example, this was also from 2009, Chicho Benitez paper. Here, suppose you have a 1% error on your angular bow. This is the angular distance measurement. And you have a 1%. If you want to get, let's say, a 4% in the variation of the parameter of the equation of state of dark energy, you'd have to go to redshift close to 1 to sample here to be able to get the precision. If you get the bow, radio bow, that is proportional directly to the Hubble function, delta H over H, and you use the same 1%, you can get pretty much this kind of precision already sampling the universe as Z equals 0.3 or so. Okay, so this difference is very important. And of course, there are the difference in cosmology. Suppose it's not symmetric, and so the theory guys start speculating on different things and so on. So that was the main objective originally at the time. And of course, this I'm going to argue later is going to be pretty obvious that the way the JPAS does is pretty different, and it provides a significant larger amount of legacy in many different areas of astrophysics. But to do that, what you need a very large field of view camera, and JPAS is about 4.5 square degrees. And this is basically just an illustration of the filters. They are spaced 100 angstroms from each other. They have a width of about 140, 145 angstroms. And you have this one in the UV here, kind of near UV, one of the near IR, and on top of that, the usual ones. Although it's been discussed which ones are going to be used, and it seems that we're tending towards an I broadband filter being the best one to go. So this kind of setup is equivalent in terms of survey speed to a 5,000 multiplex spectrograph with fibers and so on. And of course, I didn't mention this, but probably most of you know this, you need really a high number of galaxies to be able to do things, to measure the BAO and to be able to get the best odds. So we're talking here about hundreds of millions of galaxies, and near 100 million, perhaps 80 million, 86 million of them with the precision that I mentioned, the best precision of 0.3%. Actually, that's not the best, but let's say the goal precision. So this is then JPAS, in a box. So you have the goal is to get pretty much everything can be observed in the northern sky. It's very the footprint is similar to the SDSS. It had more than 8,000 square degrees, 54 narrowband filters, a blue, a red, and this actually didn't put it here, but like I said, initially there's one tray that would go from with U, G, and R, but G we are getting from Euclid, and there's a consensus that I is better than R for different reasons. In about 7 years with getting this precision. So it is, you can see that you already noticed that this kind of design, that you have this camera, allows you to study many, many different things, because every single pixel of the 1.2 gigapixel camera will have a photo spectrum. Right? So it doesn't matter what it is, and you don't need to, as you do with fibers, to pre-select the targets that you're looking at. You go and you get, and you, as long as you have software that's good enough to be able to disentangle what kind of object you're looking at, you're going to have some application, some part of astrophysics. Where it is, where is it? Is it in, it was built, it is right now near Teruel, which is the smallest capital of the province, the autonomous community, I think, Comunidade Autónoma of Aragon. It is in the mountain, Pico del Buitre, at 2,000 meters, and they built pretty much an observatory, the Havalambre Astrophysical Observatory, Havalambre Astrophysical. Okay, in English, you just invert that. The Havalambre Observatory. There, and this is a map, the location, I'm just showing here a map of, oops, sorry, I'm pointing in the wrong place, a map of the location, and this is one of the darkest place in Europe. This is light pollution. Okay, so it's a pretty good site to observe. It has been historically tested for, I guess, 2 decades. It has a medium seeing of 0.7 arc seconds. So, and it is there. I'm going to show you a little overview of this in a second. The main telescope is a 2.5 meter telescope. The field of view, this is the possible field of view, but if you take into account the effective field of view is less than that, it's going to be about 4.5, which falls in the actual camera. Okay, square degrees, but it's very, very large, has a very large attendue, which basically tells you is a combination of the width and depth, how far you can see, with a telescope. Is basically the area times the solid angle. And this one is about 26.5 meters square degrees squared, compared to Penn stars. The first one that was 15 is larger than Penn stars. So this is the main telescope, the T250, and it was also had another telescope, a 80 centimeter telescope, also with a large attendue. They can also do surveys, and it was originally thought to be used for calibration of J-PAS, and later people realized that not just that J-PAS does not really need that, but that they can actually could do some science for the local universe, and that started a survey which has been going on for a few years, called J-PLUS, the Photometric Local Universe Survey.
Renato,
yes.
Can you talk a little bit louder or increase the volume?
Yes, I'm going to get my computer. Okay.
That's
Is this
great.
better?
Great.
No?
Yes, much better. Thank you.
Thanks. So this is J-PLUS that I just mentioned, and this is the smaller set of filters, some specific to look at some particular areas of the local universe, astrophysics, O3 lines, H-alpha, star formation, and things like that. Some of the broadband filters, and some that were identical to J-PAS for calibration originally. And I'm not going to spend time on this because I don't have a lot of time, but there has been already 2 data releases, and this is the map of the coverage of J-PLUS there, and there is a lot of work on this, and there is the southern version, which is the S+, although the objective is a little bit different here. We also had at least 1 data release, I think 2019, Strawberry 2. Either they are, Roderick can confirm this, they are about to release to the public now, the second one, or they already have. But so the same telescope instruments in field. Pardon?
3rd data release.
3rd, okay.
Yes.
To the public, to the world.
Yeah.
Okay, cool. Just to have an idea of the CCDs, those CCDs, they are 9.2 by 9.2K pixels. They're pretty much effectively the largest CCDs in the world. For you to have an idea of the size of them, those are installed either one in N, one in S+, one in J+, and JPAS requires 14 of them. Okay, so it's a mosaic, a large, giant mosaic for the main camera of JPAS. That's, again, I'm showing here just to have an idea of scale. This also is one of the largest cameras that exists. I think he loses by maybe a centimeter to Pan stars, but it's really a monster. And it was actually of Brazilian responsibility. It was our responsibility to actually carry on the development. And well, the company that actually did most of the work was E2V, that is specialized in CCDs and other things. Now it's called Teledyne E2V. But it was our contribution to the project. So let me just briefly show, so you have an idea of the place. This is an aerial view of the observatory. This is the main telescope, the T250. Here you see the smaller one, the T80 for J+. There is a scene measurement here. This is the astronomer's house. Most of the structure, of course, there's a lot of stuff underground. And they actually use some of the geothermal energy for part of the usage of the OAJ. Those plants, they look like artificial, but they're actually real. Okay. So this is the aimed, and was shown to be, we did a pre-JPAS with a camera, and I'll talk in a minute, and we actually got something very similar to this to be able to test the proof of concepts related to the project. So this is a magnitude, the limiting magnitude for the different narrowband filters, this for the broadband filters. Okay, and of course, this is the colors here are not exactly right, and you see some blues and greens and yellows mixed here because of the technical issues. We cannot just put all the filters contiguous per tray. You have 4 trays currently, and this is going to change. 95% certain that this is going to change soon, because there has been a lot of discussion now of how to optimize science for the first year, but this gives you an idea of how the trays are configured. You have the bluer filters in the center and the redder on the outskirts, and this is to avoid issues with reflection from one filter to another and then passing through the other detector. And this is going to be changing because we will have to choose which trays we are going to give priority to, and we are discussing how can we do this so that we get fast science in the first year or two. So the footprint of JPAS, this is a sketch. This shows the red, blue, and yellow here are basically priorities. If you have all the time in the world, or you can wait enough, you can go all the way down to the yellow. Red is the ones that have the higher priority. And within that, the person who is in charge now of coordinating the efforts and survey strategies, Alessandro Deracliti. I think probably a lot of you know there because he spent some time in University of São Paulo. And we are discussing significantly, in the last meeting was 2 weeks ago, the seeds where we start growing the survey. This, you notice that by the design of the camera, you have 14 CCDs with 14 different filters. So you don't want to do one shot with a set of filters and then come back later 2 weeks. You want to do as fast as possible the largest area that can go around and finish with that area. So and so we're discussing what the best fields for seeds. And also the strategy has to take into account what can we do with our partners. Right now we have 2 MOUs and 1/2 MOU. I'm not sure that's considered an MOU, but we have an MOU, memorandum of understanding with the Rosita satellite, the X-ray mission. There's covering already probably halfway done to the maximum depth. the German side. We have with the German side. Sorry, I forgot to say that, and that's very important. So this map here shows the part that is inside this dark circle, this black circle here is the part that we coincide with the Rosetta, German. The other Rosetta is Russian Rosetta, and with that, we don't know. We would like to have an agreement because we actually have 6,000 square degrees with them, but the situation there is not clear. So taking this into consideration, and another MOU that I mentioned that I'm going to talk a little bit about is with WEAVE, which is a multi-fiber multiplex mission with the quasar that can benefit JPAS and vice versa in different ways. So while we're waiting for the camera to be ready, I'm going to have to go a little faster here. We put an interim camera in the big telescope and took a 1 square degree of the Aegis field, spectra, and other missions that cover this region. You know, you have X-ray, you have Galaxy, you have Chandra, you have XMM.
And after you have 5 minutes to complete.
Really? Okay. So I'm going to have to go really fast. So we decided to get this area in the sky, which the data is public. I'm going to have to go really fast here. And to do a proof of concept for redshift and other things. So this, we have 65,000 objects selected, and this is open to the world since 2019. So this is some of the photospectra as an example of this. There's a star, and you can see here, you can measure the lines and so on. I have a movie I can show you later in case there's time to show. This is just to show that the error that we want to get, the 3% error in the completeness of the sample. So with 50% completeness, you can get to the 0.3% at magnitude 22. The photo Z's are getting really, really good in comparison with the spectroscopic redshift. And the main results about this have been sent with the photo Z's by Hernan Caballero recently. Skip this. Also, we're looking at a slice in the sky, right? So if you go in redshift all the way to 0.8, we see that there's a very nice match of the photo Z's with respect to the spectroscopic Z's. I'm going to skip this movie as well. There's an idea. This is the papers that have appeared in the last 2 years. There are about 10 more, 3 or 4 being right now reviewed, and there are lots of other projects being done. I can leave this at the end. So you can see as an example, for example, you can see many of the lines, and I have to say that the evolution of machine learning has contributed significantly and kind of unexpected to the measurement of these lines. The stellar people are looking at low abundance stars, and there are works on that were not thought that would be that easy to be able to get. But you can see, here's an example of some photo spectrums, the lines here. And using this, group of galaxy evolution can, for example, try to measure the specific star formation rate in galaxies in different environments or overall. And there's one work published on that. I'm going to leave the papers there later so you can take a look. There is a significant discussion about MOX from the LSS group right now. Trying to get large-scale structure, because JPAS with that kind of precision will be able to get a fantastic map, right? A 3D map of the universe up to, 9 gigalight years out of here. So there are many, many different science that you can do with this. And machine learning is also involved in this. I'm just mentioning a few. If I'm forgetting somebody, please let me know. I'm just updating the slide. Works on very metal poor stars and in clusters, which I think for me, of course, because I like clusters, is one of the most interesting things. We are getting to a level which is pretty much unheard of. Well, it's new, not unheard of, because it's very difficult to do, which is very, very low mass clusters or groups of galaxies. You know that everyone knows that with clusters, mass function and other things. Barrier fraction can also do cosmology with clusters. It can change, determine the number of clumps of systems, which is a mass function with redshift and constrain cosmology. JPAS was predicted to be already very good. And this is a paper by Begonias Caso in the forecast, and showed that JPAS could measure things on the order of a few times 10 to the 13. And this was an actual artificial, fantastic couple with Erosita here. And this is what we actually are showing right now. This is not updated, so this is not the best plot, but this is redshift. This is the mass in 200 and 200, 10 to the 14. So this is 10 to the 13. We can get things on the order of 10 to the 12. The large errors here is because the observations from Chandra, they are not deep enough to improve this, but there's no doubt that we can get to this low mass regime, which is extremely interesting. There are 3 now codes for cluster finding. The main one that people have been using is the Miko code, which is being used by Euclid, but there are 2 other ones. PZ Wave is one of them. Let's skip this. This is the biggest cluster that we found. There's people working on galaxy evolution for this, but I'm going to skip. PZ Wave also is very good, is being very refined by Leah Dobrawa in the IAG, and there's also very light tessellation by Paulo Lopes and in Valongo. So this is an example of scaling. Of course, this scaling relation for mass and A richness. I'm not going to enter in detail about the richness, but you can actually get scaling relations for that, but you have to take this with a grain of salt, because one of the things of entering this kind of low mass regime at intermediate redshift is that, you have to assume you cannot use old, of a large cluster scaling relations to predict anything. You have to establish from first principle. So you need some other independent way of getting masses. One of the main issues now is to, before we release the cluster catalog, is to find out why there is a partial mismatch between the cluster finders and the redshift. So X-rays is in yellow here, PZ Wave is the blue, Amico is the green, and VT is the red. So not all of them coincide, and we have been, the cluster group has been working really hard to try to see what the reason for this. This is the area of that we analyzed in miniJPAS, and this is the Chandra, added Chandra pointings in X-rays. So, of course, there's some cluster counts forecasts. We're not entering details. This was predicted in 2014. There's some very recent papers. I'm just mentioning here the Risco paper showing the constraints on modified gravity theories. This is the equivalent of a G, effective G. And this is the other parameters that go into the perturbed metric there. And this is JPAS compared to Euclid, JPAS 4000, 8500. This is the 2 parameters of the equation of state of dark energy. This one's the time evolution. And you can see that JPAS, even with 4000 square degrees, is pretty good. It can be comparable to DASI or Euclid. And it seems, and this is actually very important now, but I'm going to probably skip, but it seems that our main competitiveness in terms of cosmology, in this case in particular is modified gravity, is going to be around 0.5, 0.6. Okay, compared to DASI, because DASI will take over faster. So this is what we're thinking of optimizing the filters to get in the beginning, at least. Okay, so this is DASI, Euclid, and JPAS 4000. That's the error in the effective gravity for a gravity varying cosmology. This is some papers that have been published for forecasts recently. I'll leave it here. We can send the PDF later for you to see. So we have many synergies. One of them, the weave that I mentioned before, super fast here, weave is going to look for quasars. A quasar group of weave, they need to know, they have fibers, so they need to know what a quasar is, what is a quasar, what is not a quasar, so they improve their efficiency in detecting a large number of quasars at high redshift. So JPAS in there would come very fast, woof, past there and say, this is a quasar, this is not. So they can point right, increase their sample, and then this is a region that these 2 missions coupled together, they can beat DASI. I mean, they can go further and do science over there. All right, status. So June 29th, in the middle of the first 2 peaks of the pandemics, we have first light. This first light, this the camera, just the moon here is just to give it a scale. And then there was a second peak that was really nasty, that got everything pretty slow. And there was also, during the commissioning, we had to change a couple of electronic parts that took a long time, also because of COVID. So this is done, and the commissioning is ongoing. One very briefly, the last agreement that we have is with the JWST, which will be launched in a week, maybe 10 days from now. In particular, with one field, there will be the JWST time domain field, because it is one of the regions of the sky where JWST has continuous vision. You can go there and keep monitoring over and over again. And a group that has a GTO time on that approached us. And then we proposed together some Hubble proposals, and we got them, or at least part of them. This is the area in the North Ecliptic Pole there. But of course, it's not just the two of them. This is just have an idea. We have the NEP, we didn't mention this. We didn't observe just the miniJPAS. We also observed with all filters this region, the North Ecliptic Pole, specifically for that. And during the time that we had this delay due to the instrument changing, the pieces of instrument changing, the UPAD team brought to the science level, miniJPAS level, that field, which is actually better than miniJPAS, because it did not have the constraint of having to simulate JPAS. So there's an idea of the field compared to JST, just a nice image. And this group is actually not one. We had also a meeting at the end of the next day after the JPAS meeting with most of the PIs of the other teams. New stars and X-rays, Chandra and X-rays, the Hubble that I mentioned, and many other different in radio, a lot of observations. And we are the ones who are providing the redshifts. Okay, so I can answer more questions about this later. So just so you know that the science working groups of JPAS, the coordinators are the Theory in Fundamental Physics, Jailson, Antonio Marotta from the Competencia in Madrid, Large-Scale Structure and Cosmology, Valerio Maja from the Espírito Santo, and Carlos Monteagudo, who's in Canaries. Clusters and Lensing is Alexis Finogenov from Helsinki, Eduardo Cipriano from IAG, and Chema Diego from Cantabria. And Galaxy Evolution from the IAA, Rosa Delgado, and Adriana Cortesi from the Valongo Observatory. Oh, actually, now she's in the CDPF, I think. Resolved Style Population, Simone Daflan from ON, and Vinicius Flaco, who is now in Notre Dame, not in IAG anymore. And Transients, Alvaro from ON, and Beatriz Siffert from the University of Rio. So more details on this, I'm just going to leave it here. You have the first paper of JPAS 2014, and for miniJPAS, Bono et al. Right now, recently, you can take a look. So I'll stop here, sorry for the extra 5 minutes. Thank you.
Okay, thank you, Renato. Any questions? Please use the reaction on the menu and raise your hand, or write in the chat. Any questions? Okay. Well, thank you, Renato, again. And can you unshare, please?
Sure. Thanks for the invitation. Okay, let me unshare here.
Thank you, Renato.
Okay.
You should.
Yeah, I'm not. Okay.
I think you go with your mouse to the top of the screen, and then the menu bar will show up.
Oh, okay. All right. There you go.
Thank you. Now we are going to have the talk from Mariana Penna-Lima. Mariana, can you?
Hi, everyone. Yeah. Sorry.
Yes. Yes, we can see it. Now you. Yes, you
Okay.
should. Okay, perfect.
You can see my screen? Can you see?
Yes.
Sorry. Okay, great. So good morning, everybody. I'm going to talk about the legacy survey of space and time and the Brazilian participation group. So it's not going to be a, let's say, a scientific presentation, some specific analysis, but I will discuss it's an advertisement of these collaborations. Okay. So the Very Reuven Observatory and the Rsst will catalog more stars, galaxies, and solar systems objects in the first year of the Rsst operations than all previous astronomical telescopes combined. So this is the sentence that I want to start my presentation to give you all the idea of the size and the power of this telescope, of this survey. So some features of the observatory. Sorry, it has been built in the Cerro Pachón in Chile. It has a primary mirror of 8.4 meters and, sorry, a 6.5 meter effective diameter telescope. The field of view is about 9.6 square degrees, and the survey, it will cover almost half of the sky, so 80,000 square degrees. Sorry. It's a photometric, as Rsst, it's a photometric survey. It will perform their measurements in 6 bands, U, G, R, I, Z, and Y. Okay, and each night, Rsst will cover 1/3 of the sky. The main goals of Rsst is to probe dark energy and dark matter, taking an inventory of the solar system, explore the transient optical sky, and mapping the Milky Way. These I'm going to show soon that with these different goals associated to the Rsst team, we have 8 different science collaborations. So we enter in details soon. And the science verification survey, it's programmed to start in October 2023. Some numbers about the data. As I mentioned, in the first years, it will give us more data than all telescopes combined until now. So you can imagine the amount of data, and this is a great thing, but it's also a problem. And why this is a problem? We have to deal with this data. So the way we are going to process the speed we need we'll have to process all this data, how to coed things, the speed to do all these, and to keep, and the infrastructure to keep the data, the data release we are going to produce. We have to deal with it, okay? So the raw data, we are going to have 20 terabytes per night, okay? So the data, we can divide the projects in 2 categories. We have prompt data. So every night we are going to release this prompt data, and this is something spectacular for time domain science, where you study transients, variable sources, moving objects in the solar system. So, for example, we are going to have up to 10 million alerts per night. I can't remember if it was, I think it was the first day or yesterday, we had the gravitational waves, some presentations about gravitational waves. And this is essential to have the optical counterparts when LIGO, for example, gives an alert, and you have to, you want to find the optical counterparts for this gravitational wave, what objects are emitting it, you have to deal with the transients. So, and this is something that you have a small window. In few days, 40 days, you just have 40 days to identify these objects. So this is something that every night people will be working on. And on the other side, we also have the data release data products. These are the big catalogs with the objects, galaxies, stars, quasars, galaxy clusters. So the LSST intend to provide 11 data release that we are going to be produced annually. Remember that I forgot to mention that LSST, it's a survey that it's going to take data for along 10 years, okay? In the end, the final catalog, it will have something about 15 petabytes, having 37 billion objects, and among them, 20 billion galaxies and 17 billion stars. This data will be accessible via LSST Science Platform and also via the LSST Data Access Centers. And these centers, we are going to have approximately, from now we have approximately 10 independent data access centers that we call IDEC. Some of them are going to be based in US, Chile, France, UK, and Brazil. So we are going to be one of these access centers to the data, okay? And now I'm going to talk about a short presentation about the LSST Corporation. It was created, the founded countries are US and Chile. US entered with most of roughly with the all budget needed to build the telescope. Chile is also a natural affiliated since the telescope has been built there, okay? And France and Brazil were the other two countries to join the LSST Corporation. Not with this is a decision. This was decided by the U.S. Agencies, and the contribution from France and Brazil came with some operational service. Okay, and at this time in 2015, when Brazil joined the corporation, it receives 10 positions for principal investigators, and that was the time when the BPG, the Brazilian Participation Group, was created. And in 2019, the LSST Corporation opened new opportunities to other countries to join it, but in an in-kind program. So Brazil also joined this in-kind program to have more PI positions, because 10, given our community, 10 positions is too low. And we have, we put some projects in form of the in-kind program to obtain more positions. I'm going to talk more about it. With this program, now we have 24 countries in the LSST Corporation. So, as I mentioned before, we have the Reuven Observatory, the LSST Corporation, and we have also 8 science collaborations connected to LSST. These science collaborations I listed here are the galaxies, active galactic nuclei, informatics and statistics, dark energy, solar system, strong lensing, stars, Milky Way and local volume, transient and variable start. So these are the 8 science collaborations, and to be part of the Rsst project, one must be in at least one of the science collaborations teams. Okay. So I'm going to talk more about the Dark Energy Science Collaboration Desk. Okay, it was formed in 2012, and the main goal of desk is to make high accuracy measurements of fundamental cosmological parameters using data from the Reuven Observatory. And for this, we are developing different tools and pipelines to deal with the data and perform the cosmological and astrophysical analysis. These internally, we have several working groups. I list some of them here, and you can see that the working groups are dedicated, each one are dedicated mostly in one probe, let's say weak lensing, large scale structure. I forgot to mention that the main probes of interest in DESK are weak lensing, large scale structure, galaxy clusters, supernova, okay, and inside it, we also have, for example, the modeling and combining probes working group. This is more closer to the theory, so we have to communicate and check all the needs, all things and tools that we will have to have ready when the data is available. And for these, for example, the desk, we have the simulation working group, and so they provide, they create and produce some simulations, trying to follow all the features that we are going to have with within Rsst, such that we can be prepared and deal with all the issues we know we are going to have, at least the ones we know so far. So the Brazilian participation group was formed, as I mentioned, in 2015. At first, we got 10 principal investigator positions, and now with the in-kind contribution, we were able to make this agreement, obtaining more 15 positions, such that Brazil has already 25 principal investigator positions in the Rsst. Each PI carries 4 additional junior members, and juniors, I mean students, undergraduate, graduate students, and also postdocs. So in the end, we are going to have more than 100 researchers from Brazilian institutions working in the Rsst. So how these researchers are selected? We have formed a committee from different institutions from Brazil or outside, that this team is composed, and they are, these researchers, the idea is to have a huge diversity from solar systems, Milky Way, cosmology, something closer to theory, galaxies, clusters, such that they can evaluate the applications that the researchers made and are going to make now to apply for one of the PI positions. So, so what is the main goal of BPG? Is to coordinate and also assist these researchers to conduct their work. We are forming now the Plano de Governança, and you can check, it's available here in this link, and we are forming this structure because as the number of PIs is increasing now, we are going to make we are going to organize BPG such that we can coordinate and check and follow all work that is being developed. Each researcher and junior or PI is going to be evaluated time to time. I don't know if it's going to be every year or for PI every 2 years. I have to check, such that we guarantee that the people that are in BPG are actively engaged and involved in the activities of the science collaborations they are associated and possibly in LSST. Today, the composition of BPG, and here I mentioned just the PIs, and for each PI, we have several students and postdocs associated, but for now, I'm going to list the PIs, and to each science collaboration, they are connected. So for now, we have Basílio Santiago from URGS. He is on the Stymic Way and Local Volume Science Collaboration. Júlio Camargo from the National Observatory, he's working in the Solar System Science Collaboration, and Luisa Costa from Linea ON, National Observatory, Rogério Rosenfeld from Unesp and ICTP, Sandro Vitente from UEL, Marcos Lima from USP, Valério Marra from Espírito Santo, UFES, myself from Brasilia, University of Brasilia. We are all in the Dark Energy Science collaboration. Last week, we had the LSST Brazil 2021 conference, where we give more details about not only the LSST and the Vera Observatory, but also about, we discuss about Linea, how Linea is connected to BPG. It's worth emphasizing that BPG is independent of Linea. But what are the roles of each collaboration or organization? So you can find more details in this link. All the presentations are available on YouTube. And please stay tuned, because in January 2022, we are going to make a call for all everyone that who is interested in joining BPG and LSST we are going to make a call for new participants to cover these new PI positions. Thank you very much.
Thank you, Mariana. You're talking less than 18 minutes.
Oh.
Okay, thank you. We have plenty of time for questions. If you have any, please use the reactions at the menu and raise your hand, or write in the chat. I also would like to tell you, Mariana, Renato, Felipe, and Hugo, that there will be a discussion section late this afternoon. So all speakers, the talk during the day will have the opportunity to also answer questions. Mariana, you are going to say something?
Yeah, I think I forgot to mention that when LSST released that data annually, I believe that after 2 years, each data release will be available for the community. So when I mentioned the IDEC, at least the data access in Brazil, these data are going to be available to all Brazilian community after 2 years, after each data release. I think it's after 2 years. So, this is something really important that I forgot to mention.
Okay, thank you. So I don't see any hand raised. Okay. Well, in this case, we are going to have the lunch break and return at 2 o'clock Brazilian time, 2 o'clock in the afternoon Brazilian time. Thank you, everybody. And we meet again at 2 o'clock. Bye.
Thank you. Bye-bye.
Thank you. Thank you, Mariana.